All right, thanks, Laura. Okay, I want to welcome everyone. I want to try to talk. What we're going to do here today is kind of experimental, and hopefully it will be a good learning opportunity and a good sort of break from what's going on. We're just obviously there is a lot going on right now, and that's one of the reasons why we are recording this, so people can join us later if they want to read this really cool article. But I definitely want to welcome you all and thank you for taking time from your day to do this. I think most people know each other. We have a mix of some students, a couple of scientists, a couple of citizen scientists, and Lynn representing all the teachers out there. So I'm excited that we can all do this together. So I'm going to introduce this article, and then we can talk about how we can read it together. So this article is a really nice vintage article about Aurora that was written for the British Astronomical Association, which I did not realize, but is like the amateur astronomy association in the UK. And Aurora is one of their sections, probably because in the UK you can actually see Aurora. But it definitely includes Aurora in a way that a lot of the, at least US organizations that I'm slightly more familiar with do not. And so it's written in a good way for not our usual kind of grad level, all the jargon in the world, but to try and explain Aurora with technical terms, but I think it gives us a good intro into that. And I just looked up the author a little bit because this article was a long time ago and I've not heard of the person, but he is apparently still writing articles and quite a phenomenal guy who's still involved with the British BAA. And so I'd love to hear more from him. Maybe that's something we can do. But he's written other recent articles about observing sunspots regularly for decades and decades with like binoculars and a projector. And then just recently wrote another article about the jam jar magnetometer, which is a nice, simple magnetometer that could actually work. And so I don't know too much more about his background, but I definitely think that he's got a really lot of knowledge to share. And in this way, the folks that this article was originally intended for are much like kind of citizen scientists of today, in that they were making a record of auroral observations. Okay, so I'm thinking that we can sort of go through and people can read aloud a paragraph, and then we can kind of discuss it a bit. And so each person that would be reading, after they read, they can kind of explain what they read, if there are terms that are unfamiliar or what you think this means, and sort of kind of react and ask questions, and then other people can ask questions and we can answer questions about the article. I'm not entirely sure how this will work, and I'm not entirely sure how far we'll get, but it's a really cool article. It might help to know actually if people have already read the whole article. Maybe you can drop that in the chat, and I also dropped in the chat a Google Doc that just as a place to put our comments and to take notes. And so I think we'll want to sort of establish an order. And welcome to Karina and Sarah and Jeremy that I haven't said hello to yet today. But yeah, you didn't have to read it ahead of time, but we're gonna try and read through it now. Any questions or comments on that sort of structure before we get started? Feel free to speak. I'm not sure that we need people necessarily muted automatically, but it might help, I guess. But yeah, do feel free to speak.
Hi, can you hear me? This is Jeremy.
Yes, can hear you well.
Hi, just not really a general question, but I think it would be, this paper was written, what, 30 to 40 years ago, is that correct?
Mm-hmm.
And
Mm-hmm.
as we read through it, I wonder if it wouldn't be really interesting to, for the speculation or the hypotheses that they form in the paper, just be able to fill in those blanks with what we have ultimately found out in those subsequent 30 or 40 years. Do you think that'd be kind of interesting? Just sort of, what was a mystery to them? What have we found out since then? And how did we find it out? So sort of put it in a historical context.
Yeah, that's a really good point, and certainly something. I think there is a lot that is still relevant in this paper and correct, and there might be some updates that we can offer, and there might also be some updates, like even for the figures that we might think about doing. I sort of initially got the idea of reading this article because it pertains to research that Tony and Sarah have started, plotting Aurorasaurus data and reports of Aurora, and even just updating to current observations. That would be interesting too. But yeah, we can definitely talk about the updates and questions. Any other comments? It's also totally fine if people have questions. We're all starting in a different place. We're all kind of getting something different out of this. Feel free to be like, I have no idea what that is, or there's no, we're just kind of reading it, and no judgments in that way at all. So just totally kind of appreciate people diving in and being willing to do so, and I hope that that you will enjoy it and that we can make it a little more accessible. Does anyone know the link to this article comes from a website? Does anyone know what that website is? The SAO Astrophysics Data System?
No, never heard of it.
Yes, so I was hoping I was going to put Tony on the spot here because he worked at SAO.
He got called into work today.
Observatory?
Yes, it's the Smithsonian Astrophysics Observatory, and they have this system that is like the organization of journal articles, and it's their own sort of in-house system that has existed for a long time. So you can find classic articles there. So they have some preprints from that. They've actually recently updated the format, so it does not look like it used to, but for a long, long time, say like 20 years ago, this was the way that you found articles, and there are different ways now, but it's a good reference for that. It's astrophysics, but it has all the space physics journals, so that's another sort of library reference tidbit I wanted to mention. And I don't know the full story on which articles, old articles, they actually have scanned copies of, but this one's there, so that's good. All right, anybody that would like to start with the reading is a brave volunteer.
I can start.
All right, go for it, Vincent.
Should I just do the abstract? Or is there even, okay, yeah.
Yeah, why
the
don't
first
you
page.
start with the abstract is really short. This is not like the usual format of a scientific article, and it's probably more readable as a result. But maybe you can do that and the first paragraph, if that's all right.
So then ending at axis.
Yep.
Okay, sounds good. All right. This paper describes the location of the polar aurora and how it is affected by the various types of activity. Forms of visual and radio observed auroral activity are described together with the relationship one with another. The polar aurora is related to coordinates of geomagnetic latitude and longitude, such as stellar observations are related to the geographic celestial sphere coordinates. The geomagnetic pole positions are obtained from spherical harmonic analysis of the observations from all geomagnetic observatories at 5-year intervals. Because the Earth's magnetic field is not absolutely symmetrical, the data are quoted in terms of the geomagnetic poles, the line joining which is a straight axis passing through the center of the planet. This is known as the Sun-Centered Dipole. Alternatively, and more accurately, the field may be described by the eccentric geomagnetic poles, the axis joining which does not pass through the center of the planet. At epoch 1975, the center north pole was located at 78 degrees north and 289.5 degrees east. Geomagnetic latitudes are related to the centered polar axis.
All right, great. And so maybe now you can kind of explain a little bit about what you just read or react to it or ask some questions.
So it seems like, well, okay, the first sentence is the polar aurora is related to the coordinates of geomagnetic latitude and longitude. So they're saying that, like, it's dependent on where you are in terms of latitude. So I guess that's kind of obvious, but that's what they're saying there. I have to like read it again because I wasn't really like necessarily comprehending it. So I was reading out loud.
The word geomagnetic is important there as opposed to just geographic latitude.
Right.
So it's kind of describing the pole and what orients the geomagnetic system.
Right. And they're saying that it doesn't necessarily align with the geographic north and south poles either. That they're a little offset.
Yep.
Yeah, and then it describes how they got the geomagnetic pole positions, the spherical harmonic analysis. So I guess what they're doing is they're looking at all the different I guess sort of magnetometers or geomagnetic stations, and then they're using all those data and then maybe doing some kind of special mathematical analysis with that to like triangulate where the geomagnetic poles are.
Yeah, I think the spherical harmonic analysis is just a fit to the data to make it more regular. So it's just a fancy technique for how you would fit what the data about what the magnetic field looks like, which is basically in this case mostly a dipole. So and when you get really into the research at certain level, the centered dipole is a good approximation for a lot of what we care about here. But then you can always be more precise. And in this case, like the model gets updated every 5 years because the field actually moves. So the field has moved significantly since 1975. But that's just like, it's explaining the background of how this system works.
Cool. All right.
Any other questions or comments on
Liz, is it still set at 5 years? Do they still only update it every 5 years? So is that at the, like they'll update it this year because it's 2020, they said in 75, so it's 5050, right? So they did it in 2015,
I
put it in 2020. Is that how they do
I
it?
believe that's the nominal. I believe that's the nominal order cadence. There was a recent story about the field moving faster, and they put out another update, but I don't remember the exact whether they deviated from that 5-year schedule. Does anybody know?
Looking at it online, and all of like the images. So I just Googled geomagnetic pole movement, and there's all these like data points every 5 years, and it seems like the next one is in 2020, so this year. And it looks like they've already made the observation too. So
Yeah. All right, great. All right. How about we move on? Who wants to do the next one?
I'll go.
All right, great, thanks.
The auroral oval may be defined as the plan area of the Earth's surface above which incoming electrified particles from outer space cause light to be emitted due to impact with the atmosphere. The oval is displaced relative to the magnetic pole due to the effect of the solar wind, such that along the line joining the sun with that pole in quiet magnetic conditions on the day side of the planet, the auroral oval lies between 76 degrees and 80 degrees north, and on the night side between 66 degrees and 70 degrees geomagnetic latitude, or thereby as shown in figure 1. At night, relative to any observer, the oval will reach its most southerly extent at geomagnetic midnight local time when the sun, the magnetic pole, and the observer are in the same plane. Thus, on magnetically active nights, when the oval expands, as shown in figure 2, an observer normally located south of the auroral oval is most likely to see auroral activity at his or her local magnetic midnight. In the region of the British Isles, magnetic midnight occurs at about 2200 hours local time, and the histogram of the times of peak auroral activity reported by observers shows maximum frequency to occur then, as shown in figure 3.
All right, you got figures.
Yeah, hard to read out figures.
Do you want to explain a little bit of this paragraph?
So basically what I'm reading out of the paragraph is effectively it's discussing when your optimum time to see the aurora will be based on your location, and a discussion about where geomagnetic midnight relates relative to your local time midnight, your local interpretation of midnight based on the sun, which is always an interesting one for us from an observer's perspective. Everyone always thinks that well, first there's not always a realization that the aurora moves with midnight, and this paragraph really nicely summarizes that.
Yeah, and it also further describes that geomagnetic coordinate system and how the auroral oval is not equal on that geomagnetic auroral oval system when you look from noon to midnight. And so that's kind of what's shown in figure 1, how it gets squished on the day side and a little bit extended on the night side, and how we then rotate under that. And so that's always useful, because if you're at any one place on the Earth here and the oval is kind of, you're rotating towards the oval, that curvature matters a little bit as well. And sort of figure 1 also shows the quiet auroral oval and where it's centered in geomagnetic latitude. I think when I first read this, I was thinking about having recently been to Yellowknife, Canada, and Fairbanks, and I looked up the magnetic latitude of both of them. And I think, I'm not going to remember it exactly right now, but Yellowknife is about 60, it's right at the bottom of that average auroral oval. And so the aurora really does come overhead pretty frequently. And Fairbanks is like 2 degrees lower in latitude. And I kind of feel like you can actually see that difference a little bit when it's all just kind of quiet conditions. Yeah, and all right, how about figure 3? Are you familiar with a histogram, Chris? Do you want to tell us what that might be?
Sure. So
Sorry, I was asking Chris Ratzlaff.
What's Chris? Okay, yeah, there's 2 Chris's on.
Okay.
Sorry.
Sorry, Chris. I'm not gonna let you. I know you're familiar, probably very familiar.
I'm not familiar with a histogram from this perspective.
Would you like to call a Chris?
I mean, basically what I'm reading here is peak intensity is at 2200 hours and tapering off slower after that relative to the growth of intensity, right? Or number of storms noted. So what I'm seeing is that you're more likely to have more storms after peak intensity than you are prior to peak intensity. Or prior to
Yeah.
prior to geomagnetic midnight.
I think it's important to probably understand how much time went into this plot. And I don't think it's all that much time, because the y-axis is the number of storms noted, and it kind of peaks at 16. So that's not too high. And we're talking about the UK, so maybe that's 1 year of a solar maximum type year or something like that. And so there are also fluctuations in small number statistics in here, I would say. Yeah, I wonder, Chris, did you have a good explanation for a histogram type plot? Chris Sigsby, sorry.
Oh gosh, I don't know if I can do a better job, but yeah, I think what you pointed out is that it's important to note what the length of time that they do this, because 16 is not a larger number of storms, and I have questions here too, because they talk about storms, which to a space scientist, a storm and an auroral substorm are 2 different things. But I think that they're talking about just the aurora substorm here. And yeah, I mean, they're basically taking, if you look down at a picture of the Earth from the North Pole, kind of like in figures 1 and 2, and then you have like, you can divide it up into sort of little quadrants. So like the little arrow on figure 1 where it says to sun, that would be noon, and on the opposite side of that would be midnight, and then on the left hand side that would be dusk, and then on the right hand side it would be dawn. And they're basically just going around on this histogram, the circle, like, you know, each spot on that diagram is like a local time. So as the Earth rotates underneath that, that's what your local time is. And they're just counting up. I think what Chris, like the peak intensity, like how many storms do you see the peak intensity at different local times? And as he was saying, that the greatest number here is just a little bit before midnight, but actually if you look at sort of the area underneath there, it's more filled in when you're after that peak intensity. So that maybe over in that region after about 2200 that you're more likely to see aurora, if that made sense.
Yeah, and I think the point the author was trying to make is simply that you're going to see the most storms on average at midnight, and this would be an interesting plot to remake, and we have remade from Aurorasaurus data of the time of our reports. And so a histogram plot specifically is where you are counting something into bins. And so we can take all the times, the number of reports in each local time zone relative to local midnight and make a similar kind of plot. I'm quite sure that we've done that in some past papers. But yeah, so, and that might, if we had more data, tell us if that's a statistically significant difference on both sides of midnight, but I'm not sure that it is. I think it's generally, there's some spread, and there's also the fact that the observers in this case, they might not equally make observations all throughout the night. You do tend to have some bias towards observations earlier in the night when more people are up. So that's another reason why the tail could sort of be spread towards earlier times.
Yeah, I think you made a good point there, Liz, is that because it starts out in figure 3 at 1700, which is like 1800 would be sort of in the little clock picture I described about dusk, and so you're starting from around dusk and you're only going up to midnight, and then they stop at 1 o'clock in the morning, but you know they could be going a little bit further around towards dawn, and people probably could still be seeing aurora. It's just for some reason they don't have those observations in this graph.
Yeah, and so any kind of plot, you want to understand a little bit more about the source of the data to understand how to interpret it. So that's sort of the always a good thing to take away. Anyone have more thoughts or questions about any of this discussion on this paragraph? Feel free.
Threw me off. Is in photography we have a histogram that references where the light balances are.
Yeah, there you go.
So my background is a photography histogram now.
Yeah, totally. And there's no right or wrong. It just, in this case, the histogram plot just means like there's a counting of things into bins, and that's what we call a histogram plot. So yeah,
the term actually makes more sense.
So this is
from your
sort of thing I wanted to.
The histogram as a graphic of history makes more sense than from a photography perspective.
But you also have bins there in the plot that is behind you too. So there's some similarities. Yeah.
Yeah, I mean, I would say like the plot that's behind you, it looks like you're taking different color channels and somewhere along the line they're counting up, like with on a sensor or something, the number of counts, which would indicate the intensity as a function of something.
Yeah.
On the x-axis. It's kind of the same idea.
Yeah, cool. Yeah. All right, great. Chris Sigsbee, would you possibly like to do the next paragraph?
Okay, yeah, sure, because I had a comment about this paragraph, but I think that they're going to touch on what it was in the next one. Okay, so we left off at figure 3, didn't we?
Yep.
Okay, that's a short paragraph. I'll do the next two. The Earth rotates around its geographic axis beneath the auroral oval so that the most southerly extent of the oval traces at times of quiet magnetic activity a locus at about 67 degrees geomagnetic latitude. The locus is defined as the auroral zone and represents the region of the Earth at which the aurora is most frequently seen. Unless the auroral zone is disturbed by storms and expands southwards, any aurora that does occur at local magnetic midnight in the oval will take place over the zone as shown in figure 4. Observers situated north of geomagnetic latitude 67 degrees will, because of the shape of the oval, pass under it at different local times according to their latitude. Similarly, when the oval expands southward, both the geographic position of the observer and time into the expansion phase will determine the times of contact. In quiet conditions, the observer at latitude 67 degrees will spend the longest time under the oval and is therefore most likely to detect the aurora in bad weather conditions.
Excellent. Do you want to say anything about figure 4 or those paragraphs?
So it's kind of an interesting description of it. And they do talk about the expansion southward during a magnetic storm. And and they were kind of getting at some of the things that you got out of figure the first three figures where the auroral you're rotating underneath this region, and that what the expansion of it and where you are will determine when you're likely to see it. And this kind of goes back to what I was the first paragraph, that they had sort of an unusual way of talking about the aurora as defining it as the plan area of the Earth's surface above which the incoming electrified particles cause light to be emitted. So what a scientist would normally talk about this is we talk about a magnetic footprint or a magnetic foot point. And part of the reason for this structure is if you look up into space where Earth's magnetic field extends out into space, this auroral oval would be happening on the boundary between where the magnetic field is more of a dipole magnetic field as opposed to being distorted by the solar wind. And they're kind of getting at that in this description of the oval, and how it expands during magnetic storms, but they're not quite saying that. So that was all I had to say.
Yeah, and I think also the part of the point that you're making is that the aurora is more dynamic than this, and so all of our models have some, on average, this is a statistical description of where the aurora would be overhead, and the background for the mathematics and the coordinate system and everything about that, that is useful. But then in reality, there is more dynamics of the magnetic field and the stretching and how that affects the auroral oval. That's kind of like a next level model that we don't actually have.
Yeah, and I was just looking up here because like this article was from 1980, and it's interesting. I'm trying to think history here, because I don't know if it was the first one, but it was one of the early ones. But Dynamics Explorer was a NASA mission, and it says it was launched here in 1981, and they had a global auroral. Actually see that whole auroral oval all at once from space. And so this is kind of just before that, when this paper was published.
Yeah, that's a good historical footnote as well. Any
Christine,
other
could you just say that
questions?
again really quickly? I dropped out for a second and missed that.
Oh, so yeah, and I think my thing was kind of feedbacking funny. So this paper was published in 1980, and in 1981, NASA launched a mission with two spacecraft called the Dynamics Explorer mission, and one flew kind of low in a polar orbit, and the other one flew up high. And one of the spacecraft had instruments on it so that they could image the entire auroral oval. That's hard to say. Auroral oval, from space simultaneously. And I am not quite sure, but I think that might have been the first time when we were able to see this kind of global structure. And so, it's sort of interesting to point out that this paper was published just before we were able to get this comprehensive global view from space of the aurora. Did that make sense?
Yeah, I think so. And it's also worth pointing out this article was written specifically for observers, and so it's definitely got a different bent from that. Yeah. All right. Who would like to go next?
I can try to butcher a few words in there.
All right. Thanks, Lynn.
So I'm starting at maps have been published. So maps have been published showing the isohedges or contours joining geographic points at which the aurora has equal frequency of visibility. The isohedges generally follow parallel to the lines of geomagnetic latitude. If a transect is taken from north to south through the isohedges and the data plotted against coordinates of frequency and geomagnetic latitude, the resulting frequency reduces southwards from the zone. This curve represents the probability that the Aurora Oval will expand southwards to be seen at a given magnetic latitude. Analysis of the data obtained from BAA observers confirms not only the pattern of the distribution, but also the variations in the frequency of the southern migration in each year according to the degree of solar activity, as shown in Figure 5, the shapes of the curve of the Poisson type distribution. So I looked it up. This was written in 85. They were in the middle of solar minimum. And so this is talking about you're going to have more aurora heading south during solar maximum as opposed to solar minimum is one thing that their observers found. And it shows in the Figure 5. And another thing with again with the let's see, the magnetic lines are different than our latitude and longitude lines. And so it follows the geometric latitude as opposed to our geographical latitudes.
Yes, yeah, they're talking about that being kind of the proper way to organize the system, or you see this result more clearly when you look in geomagnetic latitude. Yeah, I don't think the math details matter too much, unless somebody wants to collect a new word, isohedges. I don't know. That was a new word for me too, and we don't usually use that one too much. But yeah, I think you got it. Any other comments on this Figure 5 or that paragraph? All right. Thank you.
Hey, Liz, I'm going to have to drop off.
Okay.
Day job calls.
That's all good. Thank you, Chris. We're going to keep going. I think we are not going to, obviously we're not going to get through the whole paragraph, but paper, but thanks for trying this experiment. And yeah, hopefully everybody gets a little something out of it. So Magic sound. All right, who's interested in reading next? All right, I'm thinking
I can do
Sarah? Laura?
I can do it.
Whatever works.
All right, let me pull
All right,
it
I
back
see
up.
Sarah, so I'm gonna go
All
for
right.
it.
So normally the auroral oval lies in its quiet location. What was that? Am I in the wrong spot?
No, you're in the right spot.
Oh, okay. An activity will be seen along the 67th geomagnetic parallel and will remain there so long as the Earth's magnetic field is not disturbed. A magnetic storm causes the oval to expand southwards and the width to increase in an extent dictated by the severity of the storm. It is possible to have a solar windstorm without a magnetic storm. In this case, the Earth axis oriented component of the interplanetary field points north. If the component turns south, this triggers off the magnetic storm and the oval migrates southward until the magnetic energy has been dispersed. I think I'm lagging a little bit. But that basically just summarized how the magnetic field changes when there's a storm and whether you get a shift from your north to southward component, which we all know the southward component is what we all want to see in order to see a magnetic storm, and that will get your auroral oval to extend farther southward.
Yeah, where in this case, we're talking about the interplanetary magnetic field, not the Earth's magnetic field. Yeah. All right. Any questions on this part? I didn't quite hear you, Laura.
Nope, we're good.
All right. Would you like to go next, Laura?
You bet. There are several well-recognized types of aurora. They are quiet, thin arcs, one or more at a time, caused by quasi-trapped particles in the magnetosphere randomly dribbling into the atmosphere, partly due to minor pulsings in the magnetic field. Magnetic and ionospheric disturbances cause these arcs to burst into more active forms. I'll keep going, that was short.
Yeah, keep going. Yeah.
When the interplanetary magnetic field axial component turns south and a magnetic storm ensues, low-energy electrons produce red-colored aurorae at heights between 150 and 400 kilometers above the Earth's surface. These electrons find their way by means of magnetic field lines directly connected between the interplanetary and the Earth's fields.
All right, react.
Is this, okay, so it's saying that particles get trapped in the Earth's magnetosphere where it bumps into the interplanetary fields, and that's what makes a magnetic storm. And you can get, from low energy electrons, red aurorae way high up, traveling along magnetic field lines.
Yeah, that's it's, yeah, that's what it's saying. Storms are like much more complicated than this, so it's highlighting like to a first order, when you have some storms, you can have different types of particles and they can cause some of the more red aurora.
Is this talking about daytime aurora, or is this comprising, like, does it include the reconnection on the night side and acceleration back into the Earth's magnetosphere, back to the poles?
Yeah, that's a good question because I thought this was a little bit confusing here too. So
very large storms especially have a lot of red aurora because of a lot of those lower energy particles. So yeah. All right. Thank you, Lynn, as well, for joining us for a little break here. Great. So now it's getting into more types of aurora, more always a fun subject. Who haven't we heard from? Jeremy, would you like to read the next paragraph? Do we have Jeremy? Or is he muted? Do you have me? Does anyone hear me?
I hear you loud and clear.
Yeah, I can hear you.
I hear you.
This is Jeremy.
right.
Sorry, we're just on a call with the vet. We have to go and pick up our pet from the vet, and sort of an emergency situation. So I'm going to have to go, I'm afraid.
Oh, I'm sorry. Yeah, I hope things I hope things go well there. So
Thank you. Yeah, and thank you for this.
yeah, thank you. Thanks for finding time to. Yeah. All right. Karina, would you want to? Do you want to? I think Karina is working, so I'm not. She might not want to read.
Yeah, I'm working on the side and just listening in. So,
all right. I think it might be my turn then, and then we can go around again. Maybe we'll enter the speed round here, since maybe we'll just pique your interest to keep reading the rest of the paper. And we have this document. We can talk about questions and updates. Okay, but it's getting good here. So I'm gonna read another paragraph. Okay, high energy particles from the magnetospheric tail, on the other hand, arrive along different field lines and can penetrate down as far as 80 kilometers to produce molecular emissions having a variety of colors. The more intense the bombardment, the brighter will be the aurora, and the lower particles will be able to penetrate into the atmosphere. The mean height of a weak arc may be about 115 kilometers, reducing to 108 kilometers for a medium and 94 kilometers for a strong arc. Similarly, draperies may descend from 113 to 101 kilometers as strength increases. There are variations due to the time of occurrence, tidal conditions, and other factors. So this is an interesting paragraph because I don't fully know what it means. And yeah, the first time I read it, I made a couple of question marks, and I was going to look up some of the older references and see if there was something about tidal conditions. And also the paragraph that talks about the height of the arc descending, that makes sense because more intense arcs are going to reach down to lower altitude, but it would be nice, well, the way I'm used to it, that should probably have a reference. But yeah, so what else? Yeah, one big thing this mentions, or kind of mentions, is the fact that that it's the higher energy particles that have been processed through the magnetosphere and through the magnetic field and gain energy in this whole system, that are the ones that can go to much lower altitude. So that's important. Any questions about this paragraph?
I have a comment though. I was also a little perplexed by the tidal conditions comment, but I think what's happening in this paragraph is before we had a lot of space-based measurements of the particle populations, I think that they're trying to parse what might be happening up above just by like ground observations of the extent of, trying to estimate the heights of different arcs from the ground is I think what's happening here. And so there might be different types of aurora and different auroral forms being mixed in here because when this was written, they just didn't have, the information.
Yeah, that's a good point that there has been a lot of work before the space age on the altitudes and the different types of aurora. And so specific definitions, I think, sometimes get a bit, when we look in space, and from a different vantage point, you might call them by different names. But yeah, there's always some variations. Other comments? All right. Possibly we can do one more and then wrap up here, and you all can tell me if you want to keep going. We can schedule another read and keep going on this, or not. But I think the next paragraph is also a nice paragraph about aurora, probably a good one to stop on. So Vincent, if you're still able to read,
Yep.
why don't you take it away?
Sure. All right, discrete aurorae are forms which are thought to mark the discontinuity between polar magnetic field lines connected to the interstellar field lines and the closed field lines linked to the magnetotail. Diffuse aurorae consist of luminous cloud-like structures situated south of the discrete forms. After great storms, these appear to be zones of ionized particles which are made luminous by impacting particles. All of the above types of activity are recognizable in the BAA observing records. The following table summarizes the distribution of the most active auroral form reported on a given night by any observer in the period 1976 to 1979 for given magnetic latitude in percentages. And then there's a table right below that. So I guess what they're saying, so I just read this before. This first sentence kind of confuses me because it's saying that these like discrete aurorae, which I guess are like special types or like ones that they can like actively define, I guess, are formed by the disconnection between the magnetic field lines at the poles and then all the magnetic field lines in the magnetotail, I guess. So I guess maybe that's kind of hinting at like the reconnection concept. And then
Yeah, one thing I would say about that, if I could just interrupt you for
yep.
1 sec. The discrete are generally the higher latitude aurora where you have
Okay.
more discrete arcs. And
Okay.
there is a boundary between that and the more diffuse aurora at more equatorial lower latitudes. And the magnetic foot point at those lower latitudes ties more to closed dipolar field lines. The part about the discrete aurora mark the discontinuity, that's a little not quite as precise as we would now say it.
Okay, I see. And then it says diffuse aurora consists of luminous cloud-like structures situated south of discrete forms, which makes sense because, I mean, I've observed that too, where you see the arcs in the north, at least this is from my latitude in North Dakota, you can see the arcs in the north, and then, you know, if the storm intensifies, you just get pulsating aurora towards the zenith, which would make sense because that's what they're saying here basically.
Yeah, and this is a it's interesting to hear you say that because I've had discussions at meetings about particle precipitation and radiation about some things, and some of those different structures, like you have like your main aurora where you have like the discrete arcs and things that are produced by the current systems generating the magnetotail, but then when you get a really big magnetic storm in the radiation belts, you have plasma wave like coarse and electromagnetic ion cyclotron waves that are also knocking particles out of the radiation belts, and that might be some of those lower latitude sort of diffuse aurora structures that you're seeing.
Mm-hmm.
If that made sense.
Yeah, I know it does.
Yeah, and each of those, like, I still think diffuse and discrete is a useful first order cut at types of aurora, but then within there's many different sort of types, and the diffuse aurora really does have different forms as well, and also, as we know, shows up more at different times. So that might be in different locations, meaning as one location rotates under the auroral oval. So for instance, the sort of wave scattered, more diffuse aurora, like pulsating aurora, shows up in the morning side times a lot more. I'm not sure if that's evident in this table or discussed in this paper that much, but it might be as we keep going. So yeah, as the paper continues, it talks more about radio aurora, which is where I actually started to find this paper, because I wanted to understand what that is and how it relates to the aurora I'm more familiar with. Yeah, so I think we should pause here and let me know if you would want to keep going or you want to just read on your own. Yeah, feel free to unmute and say something about that if you like. And whether this has been helpful. So
how many pages are left in the paper? It just goes to 262.
About an equal number as what we've read. It would probably take a little while. Yeah.
Okay.
Definitely say keep going.
Yeah, I would. Yeah, I thought this was helpful, so we could keep going.
I like the whole like reading a paragraph and then kind of dissecting it instead of just like reading through it.
Mm-hmm. Cool. I think it's a good paper that you can do that, and it's just written in a nice, I think it's written in a nice way where each paragraph is really succinct. So each sentence is really succinct, and then so it's a good example of what you strive for when you write scientific.
There's a lot of information like packed into every single sentence. It's not repeating itself at all, really.
Yeah. All right. So yeah, we can probably do this again in 2 weeks, if that sounds like a good time. Yeah. To be continued.
Sounds good.
All right, great. Yeah, well, I hope everybody is hanging in there, healthy, and staying home and all that good stuff. So it's been nice to chat with people, and we're here, and we can chat more at a later time. But yeah, if you have any comments on the paper or questions that come up, you can drop them in this document. I don't know if we had any. We'll look at the chat and see if there's any comments there that should go in the document. I started trying to take notes, but I didn't fully succeed. But at least we have an order. So you all have to show up again, and we can maintain our order. Chris Ratzlaff is next. All right. Yeah. So I'll let y'all get back to your day, and I definitely, if anybody wants to talk, I can hang out for 5 minutes or more. But yeah, thank you all so much for your time.
Thank you.